Good morning. Today we are going to start the chapter Acid and Bases. Arrhenius concepts of acid and bases. Arrhenius, a Swedish chemist, was the first to define acids and bases in aqueous solutions. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, gives hydrogen ions. Accordingly, all mineral acids like HCl, HNO3, and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions. Arrhenius named these acids which dissociate completely in water as strong acids. There are other acids like acetic acid, carbonic acid, and phosphoric acid, which, when dissolved in water, do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated acid molecules. Arrhenius named these acids as weak acid. According to Arrhenius, a base is a substance which contains hydroxyl group and which, when dissolved in water, gives hydroxyl ions. Thus, substance like NaOH, KOH, when dissolved in water, dissociate completely to give hydroxyl ions. Arrhenius named these bases, which dissociate completely in water, as strong bases. There are substances which do not completely dissociate in hydroxide ions. Arrhenius named these substances as weak bases. For example, substances like NH4OH, MgOH2, AlOH3 do not dissociate completely to give OH negative ions and can be written as hydrogen ions obtained from the acid and hydroxyl ions obtained from the bases combined together to form unionized water. Arrhenius described this combination of H and OH ions as neutralization reaction. Arrhenius' concept is very simple to apply and explain a number of phenomena like neutralization, hydrolysis of salts, strength of acids and bases. However, there are certain limitations which are described below. First, Arrhenius' concept of acids and bases is applicable only in aqueous solutions. This concept fails to explain the acid or base behavior of substances in non-aqueous medium, such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Arrhenius' concept fails to explain the acidic character of substances like CO2, SO2, and SO3, etc., and basic character of substances like ammonia, sodium carbonate, calcium oxide, etc. Arrhenius' concept also fails to explain the reaction between an acid and a base in the absence of water. Although Arrhenius' concept of acid and bases suffers from a number of limitations, yet the concept is very useful and informative for an elementary approach. Bronsted-Lowry concept. Arrhenius' concept of acid and bases was further improved by Bronsted and Lowry. Both Bronsted, a Danish chemist, and a Lowry, an English chemist, in 1923 incidentally introduced the same definition for acid and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor, whereas a base is a proton acceptor. As a result, Lowry's Bronsted concept is sometimes called the proton donor acceptor concept. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the ammonium chloride. The curved arrows shows how electron must rearrange to result in the transfer of hydrogen atoms from the acid to a base. The unshared pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structures of the reactants and a product shows that the hydrogen atom, which was bonded to chlorine in the reactants, is bonded to nitrogen in the product. Thus, a proton has been transferred from chlorine to nitrogen. To act as a Bronsted-Lowry base, a species must have at least one unshared pair of valence electron so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and is a base. It is important to note that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts both as an acid as well as base is called amphoteric or amphiprotic substance. Similarly, bicarbonate ions behaves as an acid and a base. Other example of amphoteric substance is hydrogen sulfate ion. Conjugate acid-base pairs. HCl being an acid donates a proton from chloride ion, whereas ammonia being a base accept a proton and form ammonium ion. Now, the chloride ion has a tendency to accept the proton, whereas ammonium ion has a tendency to donate a proton. In other words, an acid donates a proton and then becomes a base, and a base accepts a proton and becomes an acid. Thus, a base formed from an acid is regarded as conjugate base of the acid. Similarly, the acid formed from a base is called the conjugate acid of the base. In the example above between HCl and NH3, Cl negative is the conjugate base of HCl and NH4 positive is the conjugate acid of the base NH3. Acid and bases that are related by the loss of gain of H plus ions are called conjugate acid-base pairs. Thus, Cl negative and HCl or NH4 positive and NH3 are conjugate acid-base pairs. It is clearly indicate that any acid-base reaction would involve two acids and two bases. These acid and bases are called conjugate pairs. A strong acid has a weak conjugate base and vice versa. It is further important to note that Bronsted-Lowry concept is not restricted to only neutral molecules. The concept is equally applicable to ions as well. A substance is capable of showing acidic character only if the other substance is capable of accepting the proton that is a base. For example, HCl is an acid in aqueous medium, whereas because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H plus ions from HCl. Not only neutral molecule but cations and anions may act as a acid and bases. Both Arrhenius and Bronsted-Lowry concept require an acid to be a source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acids. According to Arrhenius, a base is a substance which gives OH negative ions in solution, whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitation of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcoming of Arrhenius concepts, yet it could not answer some of the well-established reactions. For example, it cannot explain the reaction between acidic oxides like carbon dioxide, sulfur trioxide with the bases oxide like calcium oxide, barium oxide, and magnesium oxide, which take place even in the absence of water. Clearly, in the reaction between calcium oxide and sulfur trioxide, there is no proton transfer involved in the reaction. The acidic nature of compounds like BF3, FeCl3, and AlCl3 was not also explained by the Bronsted-Lowry concept. Lewis' concept of acid and bases. G.N. Lewis in 1923 proposed a more general definition of acid and bases, which is based upon the donation and acceptance of electron pair. According to Lewis' concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbital to accommodate one or more pairs of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance with unshared pair of electrons can behave as a Lewis base. Thus, the acid base or neutralization reaction involves the formation of a coordinate bond between the electron pair donor and the electron pair acceptor. Let us now discuss in detail Lewis acids. According to this concept, Lewis acids are classified as first, molecule having central atom with incomplete octet of electrons. Boron trichloride, boron trifluoride, and aluminium trichloride, etc. are acids of this type. It is clear that central boron and aluminium atoms have only 6 electrons. Second, simple cations. All the cations are short of electrons and can behave as Lewis acid. Large sized cations like sodium positive, K positive, Ca2 positive, and Ba2 positive, etc., behave as weak Lewis acid. This is because these have little tendency to accept electrons. On the other hand, small sized cations such as H positive, Ag positive, Li positive ions have a strong tendency to accept the electron pair of and are strong Lewis acids. In addition, highly charged cations have a higher tendency to accept electron pairs relative to the lower charged cation of the given metal. For example, SN4 positive is a stronger Lewis acid than SN2 positive. Third, molecule in which the central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5, and SO3 are Lewis acid, where the central metal atom can expand its valence shell. Fourth, molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represents an interesting example of a double bond between carbon and more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electron more towards it in CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient and attaches with the oxygen of hydroxide ion. Similarly, sulfur trioxide acts as a Lewis acid toward water. Lewis bases. According to this concept, Lewis bases may be classified as one of the following types of substances. First, negatively charged anionic species. All the negatively charged species are Lewis bases because they are rich of electrons and have a strong tendency to donate electron pairs. Common examples are chlorine, oxygen, OH negative, NH2 negative, etc. The greater the charge density on the anion, the stronger is the base. Second, neutral molecules with one or more than one unshared pair of electrons. Molecules with unshared pair of electrons act as Lewis bases. Third, alkenes and alkynes with multiple bonds also form coordinate bond with metal ions is organometallic compounds. Acid-base reactions according to Lewis concept. Some of the typical acid-base reactions involving the formation of a coordinate bond between a Lewis acid and a Lewis base are summarized below. First, combination between H positive and NH3. Second, combination between BF3 and F negative ion. Third, combination of calcium oxide and sulfur trioxide. It is important to note that an empty orbital is being created on the sulfur atom by moving a pair of electrons from the double bond on the oxygen atom. Fourth, combination of cupric ion with ammonia. Ushanwich concept is very useful as it classify all example of acid and base together. However, it is too general. This is because it considered even the oxidation reduction reactions as acid-base reactions. Solvent system concept. The solvent system concept of an acid and base was postulated by Caddy Ashley in 1928. It is an extension to the Lowry-Bronsted concept and is applicable to both protonic and as well as non-protonic solvents. According to this concept, an acid is a substance which either by direct dissociation or by the interaction with the solvent gives a cationic characteristic of the solvent. A base is a substance which either by direct dissociation or by the interaction with the solvent gives the anionic characteristic of the solvent. The characteristics cation and anion of the solvent are the ions produced during the autoionization. The prefix auto means itself. To illustrate this concept, for example, HCl behaves as an acid in water solvent as it gives the cationic characteristic H3O positive of water. Similarly, NH3 acts as a base in water as it gives an anionic characteristic OH negative of water. It is important to note that acetic acid behaves as an acid in water as it produces the cationic characteristic of water. Acetic acid behaves as a base in sulfuric acid as it produces the anionic characteristic HSO4 negative of the solvent sulfuric acid. Urea dissolves very readily in water and gives neutral solution. However, urea dissolves in liquid ammonia and behaves as an acid base. It gives the cationic characteristic of the solvent ammonia. Similar to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristic of the solvent with the anionic characteristic of the solvent to form the solvent molecule in non-aqueous medium. It is important to note that neutralization according to solvent system concept is reverse of autoionization reaction. Types of solvents. Solvents are classified in a number of ways on the basis of their physical and chemical properties. Broadly, there are three ways in which solvent can be classified. First, protonic and aprotic solvents. Solvents which contain hydrogen and can lose hydrogen in the form of proton are called protonic solvent. Common examples are H2O, NH3, H2S, HF, etc. Some from which solvents from which hydrogen cannot be obtained in form of proton are called aprotic solvents. Common examples are CH3CN, benzene, etc. Solvents like N2O4, SO2 and carbon tetrachloride are also called aprotic solvents. Second, acidic, basic, and amphiprotic solvents. Solvents which have a strong tendency to give protons are called acidic solvents. Common acidic solvents are sulfuric acid, hydrogen fluoride, acetic acid, etc. Solvents which have a strong affinity for protons are called basic solvents. Basic solvents are ammonia, hydrogen, pyridine, etc. Solvents which display both acidic and basic properties are called amphiprotic solvents. Examples of amphiprotic solvents are water, methyl alcohol, etc. Third, ionizing and non-ionizing solvents. Solvents which undergo self or autoionization are called ionizing solvents. Typical example of ionizing solvents are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. Solvents which do not ionize are called non-ionizing solvents. Typical examples of non-ionizing solvents are benzene, carbon tetrachloride, etc. Such solvents are nonpolar and have low dielectric constant. Relative strength of acids. The strength of protonic acid can be compared easily by the tendency of the acids to give protons. Protonic acids like HCl, H2SO4, HNO3 ionize completely to give protons, whereas acids like acetic acid, hydrogen fluoride, and HCN ionize incompletely to give protons. The acid which ionize either completely or to a very large extent are named strong acids. On the other hand, acids which ionize to a smaller extent are named weak acids. Thus, protonic acids, namely HCl, H2SO4, and HNO3, are strong acids, whereas CH3COOH, HF, and HCN are weak acid. It is the extent of ionization of an acid which measures the strength of the acid. It is convenient. The magnitude of Ka here is the equilibrium constant measures the relative strength of the acid. The stronger the acid, the larger the value of Ka. It is convenient to use the term pKa, analogous to pH, to express the dissociation of an acid. A larger value of pKa means the acid is little dissociated. It implies that acid is weak. Thus, larger the value of pKa, the weaker is the acid. Trends in acid strength. We have learned that relative strength of acid in aqueous solution can be easily expressed in terms of pKa value. The higher the value of pKa, the weaker is the acid and vice versa. The pKa values of some binary hydrides are given. Examples are pKa value for methane is 52, for ammonia is 35, for water is 14, for HCl is -7, etc. Let us evaluate how the acidity of binary hydride depends upon the nature of the compound and molecular structure or its position in the periodic table. A comparison of pK values of binary hydrides reveals that on moving from left to right across a period, the strength of the binary acid increases. For example, the acid strength of binary acids along with second period decreases as HF to H2O to NH3 to CH4. The observed trend can be easily explained on the basis of electronegativity of the element as uh, move from left to right along a period. It is very important to note that size does not change greatly across a period. With the increase in electronegativity of the central atom, the tendency to pull the electron pair from the hydrogen increases. This facilitates the release of hydrogen in the form of proton and make the hydride more acidic in character. One similar considerations we can explain how the acidic strength of binary hydride of third period decreases as a comparison of pKa values of binary hydrides reveals that the relative strength of the acid increases as one moves down the group. As inspection of the pKa reveals that hydrogen fluoride is a weaker acid than hydrogen iodide. The relative strength of halogen group 7A decreases as HF to HCl to HBr to HI. Similarly, we can see that in group 6 as well. The actual order of acidic strength down the group in the periodic table cannot be explained solely on the basis of electronegativity considerations. For example, in group 7, fluorine being the most highly electronegative element should pull the electron pair toward itself in HF. As a result, the release of hydrogen in the form of proton should be highly facilitated, making HF the strongest acid. In fact, HF is the weakest acid. The anomaly can be explained if we take into consideration the size of the central atom. As one move down the group, the electron negativity decreases, but the size of atom increases. The effect of increase of size of the atom is more than the decrease in electronegativity value of the central atom. A proton can be more easily removed from a binary hydride in which the central atom is bigger in size as compared to an atom which has a smaller size. Thus, Hi can release the proton more easily than HF. As a result, Hi is strongest acid whereas HF is the weakest acid among halogen acids. The acidic strength of hydroacids can be easily explained with the help of boron-Fazan-Haber cycle, which takes into consideration all the factors that determine the strength of the acid in water. Now, effect of solvents on the acid strength, that is leveling effect. The strength of an acid or a base depends largely on the nature of solvent used for its dissolution. One, the acidity and basicity of a protonic solvent plays an important role in choosing a solvent for a chemical reaction. The strongest acid which is available in a protonic solvent is that which results from the self-ionization of the solvent. Likewise, the strongest base available is that which results from the self-ionization of the solvent. In aqueous solution, the strongest acid which can exist and which can be available for the reaction is the hydronium ion. It means all the strong acids known to the chemist appear to have exactly equal strength in aqueous solutions. This results from the fact that acids such as perchloric, hydroiodic, hydrobromic, nitric, and hydrochloric acids all are strong proton donors than in is the hydronium ion. Thus all these acids react completely with water to give hydronium ion. It means that acid stronger than H3O positive are leveled to the strength of H3O positive when placed in aqueous solution. In other words, water levels all the strong acids, namely HClO4, Hi, HBr, HNO3 and HCl to the strength of H3O positive. Similarly, the strong bases such as hydride ion, amide ion, and ethoxide ion all react completely in aqueous solution to yield hydroxide ion. It means that all these strong bases are leveled to the strength of OH negative ions on reaction with water. In other words, solvent water levels all these strong bases to the strength of the OH negative ions. For example, when sodium hydride is added to water, a vigorous reaction occurs with a brisk evolution of hydrogen gas, and the resulting solution is found to be a solution of sodium hydroxide. Similar reaction occur when other bases like NaNH2 and sodium ethoxide are added to water. In order to compare the relative strengths of the strong acid and bases, the selection of solvent is very important. The solvent selected should be such that it ionizes the strong acids and bases to different extents. Such a solvent which ionizes the acid and bases to different extent is called a differentiating solvent. Acetic acid can be used as a differentiating solvent because strong acids like HClO4, HI, HBr, HNO3, and HCl will ionize to different extent in acetic acid. Acetic acid is a poor proton acceptor. Perchloric acid reacts completely, that is, protonates completely acetic acid, whereas other acids do not react completely because of the incomplete protonation of acetic acid by these acids. On the basis of relative strength of different ionization of these acids in acetic acid, acid can be arranged in the order HClO4 to HI to HBr to HCl to H2SO4 to HNO3. Acetic acid is a leveling solvent toward bases such as Cn negative, OH negative, OC2H5 negative, and NH2 negative. This is because acetic acid react with the bases and level them to the strength of acetate ion, that is CH3COO negative. However, strongly basic solvents such as liquid ammonia act as a differentiating solvent toward bases. Thus, it may be concluded that acidic solvents tend to differentiate between acid and level of bases, whereas basic solvents tend to differentiate between bases and level of acids. To summarize, all acid and bases stronger than the characteristic autoionized ions of solvent will be leveled off by the solvent, whereas acid or bases weaker than the autoionized ions of the solvent will remain in equilibrium. Strength of oxoacids. The hydroxides of relative metals are ionic compounds and are strong bases. However, hydroxides of non-metals are molecular compound and are acidic. The oxoacids can also be considered as the derivative of water and can be represented by the formula EOH, where E is the non-metal which determines the acidity of the compound. The strength of the oxoacid depends upon the combined effect resulting from first, size of atom E, second, electronegativity of atom E, and inductive effect of the substituent present on E. A small and highly electronegative atom E will pull away the shared pair of electrons between EO bond more towards itself. In turn, the oxygen will pull electrons from hydrogen atom in the OH bond and makes the proton to dissociate easily. This makes the compound EOH to behave as an acid. Thus, higher the electronegativity of E, the more easily the proton is lost, and consequently stronger is the oxo acid. The acidic character of the oxoacid of halogen decreases in the given order as it is evident from the pKa values. The acidities of the oxoacids are also related to the number of additional oxygen atoms, oxygens that are not part of OH groups, attached to the atom E. In these compounds, the acidity increases with increasing oxidation number of atom E. In the series of oxoacids of chlorine, the acidic strength increases in following order. All these acids have only one protonated oxygen, that is only one OH group. Perchloric acid has 3, chloric acid has 2, and chlorous acid has 1 atom additional oxygen atom. These additional oxygen atoms tend to withdraw more electron density from the hydrogen through the intervening chlorine atom. As a result, the polarity of the OH bond increases more in case of acids containing large number of oxygen atoms. In general, oxoacids without extra oxygen are weak. Oxoacids with one extra oxygen atom are moderately strong, and oxoacids with two or more extra oxygen are strong acid. Let us consider all the non-hydroxylic oxygen atoms attached to chlorine atom by a double bond. Ionization of proton from the OH bond forms an anion that is stabilized by the charge distribution over the entire ion. The greater the number of pi or double bonded O atoms, the greater is the delocalization of the charge, and consequently the stronger is the acid. The charge distribution is minimum in ClO negative and maximum in ClO4 negative. It means that ClO negative will have minimum stability and hence maximum attraction for H plus ion. This makes HOCl the weakest acid. On the other hand, HClO4 the strongest acid. We have learned that with the increase of in the oxidation state, the central metal atom, the acidity of the acid increases. The same argument of increased acidity with increase in oxidation state can be extended to nitrogen acids and in case of sulfur acid as well. However, the generalization does not apply in case of oxoacids of phosphorus. The important non-oxoacids of phosphorus are H3PO2, H3PO3, and H3PO4, in which the oxidation number of phosphorus is +1, +2, +3 respectively. However, experimentally, all the oxoacids of phosphorus have been found to be weak acid with the increasing acidic strength. In order, oxidation number of P +1, 2 +2, 2 +3. The discrepancy in their acidic strength can also be explained if we take into consideration the molecular structure of this acid as shown below, which contains the pH and P double bond O bonds rather than the expected POH linkage only. Now, acid strength of hydrate cations. Hydroxide of relative metals are strong base, whereas hydroxides of non-metals are acidic. Hydroxide of elements near the borderline between the metals and non-metals in periodic table are amphoteric. It means that they can react either as acids or as bases. With acids, they react as bases, and with bases, they react as acids. Aluminium hydroxide offer a beautiful example. In order to understand why aluminium hydroxide is amphoteric, we must consider the hydrated cation AlH2O6 3 positive. When to the solution, the hydrated ion, a strong base such as potassium hydroxide, is added. Protons are transferred from hydrated ion to the base, and the addition of OH negative ion shifts to all four equilibria shown above to the right. As hydroxide ions are added to a solution containing hydrated ion, insoluble AlH2O3OH3, written frequently as AlOH3, is precipitated out, which dissolve in the presence of excess of OH negative ions. If a solution of a strong acid is added to a solution containing AlOH negative ions, H plus react with OH negative ions to form water. As OH negative is removed, All four equilibria shift to left. An insoluble AlH2O3 NOH3 precipitates and then redissolves. Since AlH2O3 OH3 react with either acid or base, it is amphoteric in nature. It is important to note that when protons are transferred from hydrated cations and on OH bonds breaks just as it does when protons are transferred from oxo acid, equilibrium constant for the hydrolysis of hydrated cations can be measured. Now, thus, the order of acidity among alkali metal ions is K positive to Na positive to Li positive. It is obvious that the acidity of hydrated cations of alkali and alkaline earth metals decrease down the group of the periodic table. If radii and electronegativity are similar, as in the case of Na positive and Ca2 positive, then the higher the charge of the cation, the more acidic the hydrated ion. If one moves across a row of the periodic table from left to right, ionic radius decreases and charge increases. As a result, acidity of the hydrated cations increases across a row. If charge and radius are similar, the greater the electronegativity of the metal, the more acidic the hydrated cation. Let us compare the case of Mg2 positive and Zn2 positive. In case of zinc, the electronegativity is more, hence the cationic zinc is more acidic than magnesium. The hydrated Al3 positive ions with the high charge, small radius and relatively high electronegativity for a metal is by far the most acidic cation. Role of solvent on the strength of Lewis acids and bases. A solvent plays an important role on the strength of Lewis acid and base. A Lewis acid on hydrolysis may produce an acid stronger than the Lewis acid itself. For example, boron trichloride, which is a Lewis acid, undergoes hydrolysis with the evolution of hydrogen chloride. The sequence of steps involved in the hydrolysis are outlined below. First, the first step involves the attack of photo molecule on the vacant 2p orbital of boron. A lone pair of electrons from water is donated to the empty orbital of boron with the formation of coordinate bond. Second, the second step involves a loss of one HCl molecule. In doing so, one of the chlorine of BCl3 is replaced by one OH group. Third, the third step involves the repetition of the above steps till the chlorines are replaced by hydroxyl groups and one get boric acid. Another interesting example where the role of the solvent is greatly appreciated is the hydrolysis of silicon tetrachloride to offered silicic acid. The distinguishing feature in the hydrolysis of boron trichloride and silicon tetrachloride is presence of vacant 3d orbital in case of silicon. The mechanism of hydrolysis is the same, expecting that the water molecule attacks the vacant 3d orbital of silicon, forming an adduct involving a coordinate bond between silicon and oxygen. The adduct formed loses HCl molecule in steps till all the chlorines atoms are replaced by OH group, yielding finally silicic acid.